Mm. Welcome back, everyone. Let's continue our class of foundation engineering. We are still on the chapter number 1, and we will do one more time this part, density and compaction. We did the previous video was about this point. This video as well will be about this point. So part 2 of this density and compaction. Okay. Soil compaction. Last time we talked about density, different relationship between water content, unit weight, density. Okay. And this time, in this video, we will try to talk about soil compaction, how compaction is done in the lab, and how we check the degree of compaction in the field, construction field. Okay. So before the construction of any foundation, building, for example, building foundation, it's very important to compact newly constructed embankment and natural subgrade so that it can meet a specification, some very important specification considering the water content limitation. Okay, so there are some laboratory tests. Typically, laboratory compaction test on the foundation soil is conducted, okay, beforehand. These lab tests will help to establish appropriate field compaction specification. But anyway, this is about compaction, and there are more detail about this compaction in my soil mechanics class. So I suggest you to visit the soil mechanics class. You will get more detail about compaction. Okay. So there are two common tests for this compaction in the lab. You can do standard Proctor compaction test and modified Proctor compaction test. The modified one is the difference between these two is just about the compaction energy. Okay, compaction energy in the modified Proctor one is higher, much higher than the standard Proctor one. That's all. You can find more detail in my soil mechanics class. Okay, so two types. So in this section, this video, we will try to summarize the lab compaction, computation about lab compaction, and give some detail about experimental information. Okay, so first, the lab compaction. How does it work? This is really a rough summary. Okay, more detail are in my soil mechanics class. So during lab compaction test, soil sample from foundation soil, you have to take the foundation soil, okay, not any soil. So you take the soil sample from the foundation soil and you compact it under various water content using standard compaction. Okay, this equipment For example, this equipment is for the standard compaction. This is the mold and this is the hammer. Okay. Again, more detailed soil mechanics class. Okay. So each trial, because you will do the test with several tests as stated here. Okay. For each sample, each trial, the weight of compacted soil filling the standard mold, this mold, and the water content are recorded. Okay. You record them and you can write and you can do a table like this. Okay. So mass of compacted soil and the mold, both together. For example, here we have, for example, four trials, four tests. Okay. This one, the mass of the soil and the mold all together is this one in gram. So 5.8 something kilogram. And compacted water content. So it means for each test, the water content, okay, 4.48%, increasing like this. And the unit weight, this unit weight is the bulk unit weight, the total unit weight, or if you want, again, the wet unit weight. Okay, so after that, you have here dry unit weight. Okay, from this one and the water content, you can obtain the dry unit weight. Okay, and this one also, some people do, they dry unit weight at 100% degree of saturation. Okay, so you get a table like this from all the tests you do. So this bulk unit weight is giving this one, this formula. This formula is giving you this. The total weight, this weight, divided by the total volume of the mold. Okay. And after obtaining this, you can then make a graph, this kind of graph, the water content versus dry unit weight. The dry one is used here, not the wet one, because the dry unit weight is the unit weight that gauges the compaction, the degree of compaction. It will tell us if the compaction is well done or not. Okay, so I will keep this here. Okay. Here is an example. So plot the compaction curve for data provided in this column 2. So, and 4, 2 and 4. Okay, water content, dry unit weight. Okay, actually this is just here already. You don't need to do it, but you can try. You will see, you will obtain this curve, this shape. Okay, and after that, from this table, after that, determine the maximum dry unit weight achieved under the standard compaction condition and the corresponding optimum water content. So the optimum water content is the water content that corresponds to the maximum dry unit weight. So after plotting the curve like this, you can then try to know the coordinate of this point, the summit. the maximum here. The water content corresponding to this point here will be the optimum water content. Optimum water content, okay? And the dry unit weight corresponding to this point about here will be the maximum dry unit weight. These are the information we need when we do compaction in the lab. These two are the information needed. Okay, so from this curve, we can read and understand easily and obtain these two information. So note that here, this figure, the mold here has 400 and 4,020 to 200 grams, and the volume is 940 milliliters. So if you have the weight of the mold, you see here, what we have here is what we have is mass, this mass of the mold and the soil. For example, here, the first trial, 5,873. So if you take 873 minus 4,200, okay, because this one is the mass of the mold. What you will obtain will be the mass of the soil. Okay, the mass of the soil in that case, in here, it will be 1,673. Okay, about 1 kilogram, 1 kilogram, 600, 1.6 kilogram. Okay, then you can utilize the formula, the volume, the mass divided by volume. But if you want this unit weight in kilonewton, the mass you have here, you have to convert it in weight. So kilogram multiplied by G, the gravity, 9.81, you obtain in Newton. Then you convert from Newton to kilonewton. So the mass weight, anyway, the mass here will be divided by the volume to obtain the unit weight. Okay, I think you can do that. By using these two formula, then you can obtain the dry unit weight. So after doing that, we can read directly from this. Okay, using this formula, we can calculate the bulk unit weight and the dry unit weight, both. So the maximum dry unit weight, by reading this, we can say it is about 17.1. Okay, 17.1. Because here is 17.00, here is 17.2. So it kind of like middle of these two. Okay, so 17.1 kilonewton per cubic meter. And the optimum water content will be about 10. So 10%. So these are the information we need each time you do the Proctor test in the lab. So please remember, if you want more detail about this, you can obtain from my soil mechanics class and how to do the test, everything. Okay, so if I keep this here, the maximum dry unit weight and the optimum water content, optimum Proctor. Okay, sometime some people use this curve, this data to plot a curve. If you do that, you will obtain something like this one. This curve is this line, the name is zero air void curve. Okay, but it's not really necessary for you to do that. You don't have to do that. But if you want to do, you have to use this formula, and then you can obtain. So anyway, based on the result of the lab test, I mean the maximum dry unit weight and the optimum water content, you can now give some specification for the field test. Okay, based on the lab test, you have to give the specification for the field test. So normally, the ideal move, the ideal thing to do is to obtain exactly same value on the field. You do the compaction on the field and you obtain exactly same maximum dry unit weight and optimum water content when you will do your compaction on the field. But it's difficult to obtain exactly same value. Normally, a margin is given. So for depending on the project you are dealing with, compaction or dry unit weight in the field must be around 98%. Sometimes it's 95%. Sometimes it depends actually on the project. If the project is a very important project, very huge project, then the percentage is high. Okay, so if I think there is a mistake here. So if we try to calculate this, the 17.1 maximum dry unit weight, you will see that you will obtain around 16. This is a mistake, okay? We will correct it very soon. 16.76. The 7 should not be here. Okay, so it means on the field, depending on the project, you can give specification for the field compaction. If the result of the field compaction is less than this, then the quality control, they have to tell that, okay, in this place, at this place, you have to do the compaction. It's not good. If you obtain, for example, 15, then it's really not good. Okay. And the water content also should be within 2%, the difference, within 2%. So the optimum water content here is 10%. It means on the field, you have to try to be between like a difference of 2%. It will be between 8 and 12%. 8%, 12%. Okay, so how does it work exactly? After laying, because on the field, the compaction is done maybe layer by layer. So the ruler will, first you have to put water on it, on the soil. Okay, the amount of water is calculated using this water content, because remember, water content is just weight of water divided by weight of soil. So if you know the natural water content of the soil, you can judge on like how much the amount of water you have to add to obtain this optimum water content. Okay, so pouring the water, some tank can do that, and after that the ruler machine that the machine that are doing compaction, the field compaction, will do the compaction, and at the end you have to obtain the maximum dry unit weight around this 98%. Sometimes it's not always 98%. Here it should be 16. Let's correct this before we continue. 16.76. Okay. Yeah. So after doing that now, how can you now check if the field compaction is good? I hope you understand everything now. After doing the lab test, you obtain the maximum dry unit weight and the optimum water content. You can say, okay, we will try to have the same value on the field as well. So you can try to decide on the water content, optimum water content, by adding water, the amount of water you will add. And the compaction energy, please check my class of soil mechanics. It will be better. It will explain everything. Compaction energy will be decided also depending on the ruler that will, the machine that will compact the soil on the field. So if you do that, how will you know if this percentage is respected? This is another issue. So there are methods, there are ways to check this if the compaction is right, is if the percentage is good. Okay, so that's why we will talk here about evaluation of field compaction. This is how quality control is done for the compaction. Okay, so unit weight of compacted in situ soil and newly laid embankment can be evaluated using many methods. So after doing the field compaction, after completing the field compaction, you can check it using many methods. There are several methods. In this video, I will talk about three of them. I will introduce three methods, and we will take one example using one of them. So the first one is sandstone sand contest. Sand contest, which is this using this equipment. Okay, sand cone test. Okay, the cone. This is a cone, right? And in this container, you put sand inside. Okay, but before putting the sand, you have to know everything about the sand, the unit weight, the all the information of the sand. Okay, and this plate, you can see here the shape here of this opening is corresponding exactly to this, the opening, the top of this, or how to say, the bottom of this cone, right? So you can imagine that it will be above this. Okay, so this is how it works. You put here, and this is like a van to close it. So the sand will be inside here, and you can open the van to let it go or what. So it means you have to dig to make a hole in your compacted soil. Okay, in your compacted soil, and leave the sand put the sand inside. Here is how it works. This hole, you make this hole in your compacted soil. And this plate, you see this gray part is this plate. Okay? And this is the core, this one, this part. So this is exactly what is here. This is sand. Okay? Suppose that you know the unit weight of this sand. Okay? Then you dig, you make the hole in your compacted soil, compacted ground. And the soil in this hole, the soil from this hole, you keep it very well, safely. You put it in the container because you will use it in the lab later. You will need to weight that soil to know the weight, the mass of the soil. Okay? Here, it will give us, because we know the initial volume. Okay? Here, weight before the sun. And here is after. Maybe the level was here, and all this part went in the hole. So by doing that, we know the volume, we will know the volume of the hole. And by knowing the volume of this hole, and the soil from this hole will give us the mass of the hole. It will give us the mass of the hole. So by knowing the mass of the hole, knowing the mass from the hole, the mass of the soil from the hole, and knowing the volume of the hole, we can have the unit weight of the soil, the compacted soil. Okay, it will give us the bulk unit weight, and then we can obtain also the dry unit weight by trying to dry over the soil from this hole. We dry it and weight it again. Then you do the weight, the wet weight minus dry weight, you will obtain the weight of the water, right? And the weight of the water, we will use that to obtain water content. And from the water content, you can obtain the dry unit weight. Dry water content and the bulk unit weight can give you, we have seen the formula for that, right? It can give you the dry unit weight. Okay. The second one is rubber balloon test. Rubber balloon test. You see this, maybe this is a balloon. Actually, not one, several balloons here. And this balloon, the principle is same as this one. You make a hole, same. But here, instead of using sand, we push like this, like pump, and the balloon will expand in everywhere in the void, in the hole made in the compacted soil. Okay, it goes like this. You make a hole, okay, same as this one. About after making the hole, this balloon you put it. Actually, there are several color. For example, maybe this one is more visible. This white. So it's just like a plastic bag. The plastic bag you will put at the bottom of this device. Okay. So the balloon will take the shape, since it is plastic, it can easily take the shape of this hole. So it will take the shape of this hole, and by pushing, you can directly obtain the volume of this void. Okay. So if you obtain the volume of this void, again, it will be same principle like this one. The soil from this void you have to take it, collect the soil, and go and try to know the weight of the soil, the mass of the soil. And this divide will give you the volume of this soil. Since the soil is coming from this hole, so it means it was the initial volume, compacted volume of the soil. Okay, so the mass of the soil from this hole divided by the volume of this hole, it will give you the compacted humid weight. Okay, it will give you the compacted unit weight, but bulk unit weight. Then you go to dry the soil from this hole, dry it. If you have the wet unit weight, you have to the wet weight, go and dry again, you will obtain the dry weight. So wet weight minus dry weight, you will obtain the weight of the water that was in the soil. And if you have the weight of the water, you can obtain the water content. From the wet unit weight and the water content, you can obtain the dry unit weight. Same principle, same philosophy here. Only the way to obtain the volume is different. Okay. Okay, let's continue. The third method is here, the nuclear gauge method. It's same here. This same here. Third method, the nuclear gauge method. As you can see, the name is it's nuclear. It's using nuclear. This device. Okay. This device, this stick, there is one of them will go inside. Like small hole. You make a small hole. There is a tool for that. As you can see, this is compacted soil. And we want to check. Actually, this photo, I took it myself with my cell phone. Okay, it was a big project. I will show you some photos right now. I took this photo myself. So this, when I was doing master degree in Burkina Faso, in my country. So this project is like it was a very big project. So this kind of device, this device is used mainly for very important project, because this device is quite like very expensive actually, and you need license to manipulate this. So that's why the guy who is manipulating this, it wasn't me, because I didn't have license to manipulate this. So but this, the copybook you can see here, this was me. This is mine. I was taking note. I was writing, but I cannot manipulate it because I didn't have license. So the nuclear gauge method, it giving you all the information at the same time. You don't need to go and wait the sample. You don't need to dig, make a hole in the ground. No, it's very convenient. It will give you the unit weight, the wet unit weight, the water content, many information it will give you. Okay. So compared to the other method are really cheap. This one, sand cone test and rubber balloon test. These two are cheap and easy to master. You don't need long training. You don't need even license to perform these sometimes. But that depends in the country where you are really. But this one for sure you need license to operate this device, because it's somehow dangerous. It's nuclear. Okay, and this one is used only for very important project. This project is this project in my country. we built this interchange. This interchange, during the construction of this interchange, I took these photos actually. This one is not from me, this one is from Google, but this photo, I took it by myself, my phone. And this is actually, this photo was this one. You see the foundation of this. This is like one of these bridges in here. I don't remember which one of them. Okay. One of these bridges, the bridge pier. Okay. So after building, making the foundation, this is the foundation of this. As you can see here, the difference, the difference between this level and here. So we have to compact around this foundation. For those who think that for foundation we don't need to compact, that is not true. We have to compact. Otherwise, the water can destroy this foundation very easily. This water can enter here. It will be not good for your foundation. Okay, so the soil around this foundation needed to be compacted very well. As you can see, it's a very huge project, very expensive project. Okay, so I was part of geotechnical team when I was doing master degree, okay, professional master degree. And this is me. Funny, right? This is me when the same someone took the photo, but this one is me. Okay. And I was taking note. This is my copybook. So there are many methods to check the quality if the compaction is good or not. Okay. This one is very convenient. Here you have three of them: sand cone test, rubber balloon test, and the nuclear gauge method. So we'll try to do one example for this. Estimate the field dry unit weight of a given embankment field based on the cone sand test. Okay. So we will use the first method to estimate it. So first step, solution. The first step is to determine the density of the sand in the laboratory, because the sand in the bottle, in the device itself, we have to know the characteristic of the sand. So we have to know the density of that sand. Okay, not the sand in the hole, not the soil from the hole. The sand that is in the device itself. Okay, so we use uniformly graded sand. For example, this in USA they use this, for example, Ottawa sand. This is typical sand, for just for your information. You don't have to use this one, of course, but you have to use very uniformly graded sand so that it can minimize mistake. Okay, and the sand should not be sensitive to compaction. So this sand is used for calibration. You put it in the device. So by doing that, this kind of sand, the density of this sand, which is assumed to be like constant, not changing, can be first established based on the measurement made with the mold. Okay, a known volume, the mold, for example, 940 milliliter. Okay, here is how it goes. So the mold, we will use a mold. Mold, the diameter of the mold is this. The height of the mold is this. So you have the volume of the mold is here, right? So technically, diameter and height, if you have this diameter and this height, you can calculate. But here is cubic is centimeter. If you use this you will obtain it in cubic centimeter. Don't forget that this is given in milliliter. Okay. And you know also the mass of the mold. The mass of the empty mold is here. So the mass of the sand, this is only for this test. So mass of the sand in the mold with the mold together is this one. So it means if you take this mass, because mold and sand, minus this one, you will obtain the mass of the sand only. Okay. The volume of the mold here is in cubic centimeter. Please don't mistake. Here is milliliter. So you can convert. So by knowing the volume of the mold now in cubic centimeter, you can obtain the density of the sand, because the volume, this volume will be occupied by the sand with this mass. The mass you will obtain 5,602 minus 4,252. You will obtain 1,350 grams. This is the mass of the sand. So this mass divided by this volume, you will obtain this density. This density. It means you didn't start this test yet. You are just doing the calibration of your sand, the sand that is you will use for the test. This is the first step. Okay. I'm not sure if you understand. Let me go back here so that you can understand what I'm talking about. The sand here, this sand, okay? You determine the unit weight of the sand first, this sand first, okay? By not putting it here, this device will not give you the unit weight of the sand. You have to use the mold, this mold. Let me go back, this one, okay? If you know the volume of this mold and you know the weight of the mold, empty mold, after knowing the weight of the mold plus soil, because you will put the sand in this mold and you go to weight the sand and the mold together. So if you take that weight minus the weight of the empty mold, you will obtain the mass of the sand. This mass of the sand divided by the volume of the mold, it will give you the unit weight. In that case, you have the unit weight, dry unit weight of the sand calibration for this sand. This sand here. Okay. So let's go back. I think I went too much back. It is here. We were here. Okay. So this is how you obtain the unit weight. So let's keep this value of the dry unit weight of the sand. Okay. Calibration. Sand for calibration. This unit weight, we keep it here. This is in grams per cubic centimeter, and this is kilogram per cubic meter. Okay. Okay. Then we go for this next step. The second step is to determine the mass of the sun to fill the cone. What is the mass of the sun for filling the cone? Only the cone, okay? We need to know that. That is the second step. So this figure, this cone, this cone, we need to know what is the mass for filling this cone. And you will know why we need to know that. You see this van, you open it and you let the sun go until this one is full, the cone is full, then it stops. You can then close the van and remove, and you know the weight. Okay, so to know that, the mass of the jar and cone before filling the cone. This is the jar. So everything before filling, it was 3,516 grams. Okay, then the mass of the jar, cone, and sun after filling the cone. You have this. After the cone is filled, 1,934 grams. Then you can determine the mass of the sun filling the cone by doing this minus this. 3,000, you can calculate by yourself. 3,516 minus 1,934. You will obtain exactly 1,582. Okay. So this is the mass to fill the cone, the mass of the, sorry. Technically, it means you have your sand here. The sand in this, first this, you don't invest this cone like this. You put it in this way, not in this way. Okay, put it in this way, and you weight it. It means the sand is in this jar already, and everything will be 3,516 grams. Then now you put it in this way, like this, and you open the one, the sand will go down here until it stop running. Once it stop running, it means the cone is full, right? Then you can close the van. Close the van and go and wait again. The everything, weight it again to know the weight, the mass. Then this mass, the beginning minus the new mass when the soil is reduced, you will get the weight of the sun here. So step number 3, you can go now to measure in field measurement. You make the hole, you place this apparatus on the hole, tug the hole first, of course, and if you make the hole, the soil from this hole, you don't throw it, you have to take it to go and measure it. Okay, then you place this apparatus, the sand cone apparatus, on the hole. You place it, but of course, before placing it, you have to weigh it and know the weight, the mass of everything. Okay, before placing it on the hole, You have to know the mass. Know the mass of the apparatus plus the soil inside. And after that, you place it on the hole like this. But before placing, you have to know. Because if you place, you open the van, the soil will run in the hole. Okay? Then, as I said, the in-situ soil removed from the hole is now collected and weighed. You collect it and go and keep it because you need to know the mass, the weight of it. So the volume of the hole created this hole is estimated by knowing the amount of calibrated sand required to fill this hole. Okay, so after making this, putting this apparatus on the hole, you open the hole and this sand will run inside. After, if it is full, it will stop running, of course. Then you close it and you go to wait again. The previous, before opening, it was here. So you know the way. Wait with sand before opening this van. And after opening and after filling this, if it is full, after filling the hole, but before filling the hole, of course, the cone also, it will pass the cone, fill the hole, and fill the cone. Okay, and you go to weight it again. Weight this. After filling everything, you will remove the apparatus and go to weight it. So the new weight will be, of course, less than the first one. So the previous one minus the new weight will give you the weight of this total, this one and this one. And of course, you know already the weight to fill the cone. So by obtaining, making the result minus the weight to fill the cone, you will obtain the weight of soil in here. And if you know the weight of soil in this hole, you will know the volume of this hole because you know already the unit weight of this sand. Quite complex, difficult for some people. For example, if we have, before the test, we have here, the sand is here, the level of sand is here, and the mass is 6,538 grams. Okay, means it was here. And after opening, and filling both the hole and the cone, means this only this amount of soil, you will have 4,325 grams. So now you take this one minus this one. How much you will obtain? 6,538 minus 4,325. You will obtain about 2,213. But this 2,213 is the mass of the soil in the cone plus the mass of the soil in the hole. But if you remember, the mass to fill this cone is here. So you do minus 1,580 2. You will obtain about this mass of collected soil. This mass is not the mass of this one, okay? This mass is the mass of the collected soil. The soil you took from this hole, okay? The soil you will take from this hole, not the soil in this, the sand in this hole. We will come back on that later. So 870 grams, the soil that was in this hole. Now the mass, okay, this is now what we have. Mass of the sand in the hole plus the cone means this one. This is what I was talking about now. This, the mass of this plus the mass of this. You do this one minus this one, you will obtain this 2213. Okay, then you take this, you do minus this, because the mass of this cone is 1582. Then you will obtain 631 grams. So this 631 is the mass of the sand in this hole. Since you know the unit weight of this sand, which is here, from the unit weight and the weight, you can know the volume of this. Okay, so you do the 631 divided by this unit weight here. It will give you the volume. So this means this is the volume of this hole. And don't forget that the mass you took from this hole, the collected mass of collected soil from this hole, is here. So by taking this mass dividing by the volume of the hole, like this, you see 870 divided by this one 438.9, it will give you the unit weight of the soil collected from this hole. This unit weight, the bulk unit weight, because the soil collected from this hole is wet, not dry. Okay, so we will write the bulk unit weight here. We keep it here, the new result. So now the last step you have to do, you have to measure the water content. Okay, water content, the soil you collected from the hole now. Okay, you take that soil and you go weight it, know the weight. You already know the weight, the total weight, the humid, the wet weight, the soil. Then you go and dry it and try to find the dry unit, the dry weight. And you do wet weight minus dry weight, you will obtain the water content. But sometimes some people do like several samples. You dry several samples and try to measure. For example, here we have 3 trials. 1, 2, 3. From the same soil, you take just small samples from the soil collected from the hole. Soil collected from the hole. So the mass of the container, it goes like this. This is also me, but this is when I was bachelor student. So this container, as you can see here, this fixed container, the mass of the container plus the wet soil. First trial, this one. Second trial, this one. So you take 3 container, 1, 2, 3, for example, and you take small, the soil from the hole, you take small, just put in each container and weight it, wet weight. After that, you dry it in the oven for 1 day, for example. It will dry for sure. Okay, so mass of the dry soil after drying it, this is what you obtain. There is no way that you can obtain this is higher than the previous one. Okay, if you obtain that, then you have a problem. Then you know the mass of the container, right? The mass of the container is easy to obtain because empty container, or you just do the mass of dry wet weight minus dry weight, and you will obtain the water content, the mass of the water that was in this soil. Okay, for example, for the first trial, if you do 146.54 minus 144.63, you will obtain 1.91. This is the mass of the water that was in this soil for the first trial. Okay, so you can do that to obtain water content for each kg. Each of them, each trial. This one gives us 6.16%. This one gives us 4.52%. This one gives us 6.13% as water content. Okay, so then you take average water content by additioning these three and dividing by 3. Okay, 1/3 multiplied by this addition. You will obtain average 5.6% as water content. But some people don't do that. They just do only one test, one sample, and that's all. So if you have now water content and you have the bulk unit weight, from this equation, this formula, you can obtain the dry unit weight, right? Bulk unit weight, water content. Okay, by using this formula, you can obtain the dry unit weight, which is here. Okay, 1877 kilogram per cubic meter. Okay, and in kilonewton per cubic meter, it will be something like this: 18.39 kilonewton per cubic meter. Okay, that's all for this. I hope it is clear. This is actually how it works for quality control, or after compacting your soil, you need to check if the compaction is well done or not. Okay, thank you very much for your time, and see you next time. Thank you.